Good afternoon. Let's get started. Today, Max and I are going to talk about cloud deep learning using Microsoft R Server and high-performance GPUs in the public cloud. So first off, a little bit of background and motivation, right? Why do we care about deep learning? In the past couple of days, I hope from Satya's, Joseph's keynote presentations, you have learned a lot of our industry trends where we accumulate massive amounts of data. And the only invariance here is really the scarcity of our time. And so there's the need to extract deep intelligence from the data is increasing. And deep learning is really a essential technology to do that, right? And in the past few years, we have seen a lot of progress and breakthroughs in the fields like computer vision and speech, where deep learning is the key technology there. Why do we care about the GPU? GPU is really the engine in the last decade to drive deep learning progresses. And why do we care about cloud deep learning? In the next 9 to 10 years, we're going to see data continue to grow exponentially. Yesterday, you heard Satya mentioned last year, humankind has 10 zettabytes of data, and by 2025, that number will grow to 180 zettabytes. So most of this data will either be born in the cloud or live in the cloud. So it is crucial to have a cutting-edge, sophisticated cloud deep learning ecosystem to do deep learning. And with the newly announced Azure N-series GPU instances, we have the ability to do that now. And why do we care about MXNet, open source deep learning framework? You may have these questions, especially you have seen Frank's talk earlier about CNTK. By show of hands, how many of you were in the CNTK talk earlier this afternoon? Some of you, right? And each of these frameworks have its own strengths. We really love CNTK. It has cutting-edge performance, leading-edge scalability. MXNet is interesting as well because it has rich binding for different languages of R and Python, for example. The bigger point is, though, we're building an open platform. We use a lot of open source projects. We contribute a lot of code back to open source. And we want to enable people to be able to pick and choose based on their preference and their needs. And finally, why do we care about R? R is the so-called golden child of data science. It has been around for a while, especially in academia. But its popularity really picked up with the rise of big data in the last few years, right? This August IEEE Spectrum, you see R ranked number 5 in all computer programming languages. And it is the only language specifically designed to deal with data in the top 10. Right? So we want to show in this talk how we can develop a consistent, unified workflow using R doing deep learning in the cloud. So a little bit of a review of the technology stack of a cloud GPU VM, right? At the bottom is the hardware. In this case, we have cutting-edge NVIDIA Tesla K80 GPU, as well as the CPU, which every VM has, and then OS. In this case, we support both Windows and Ubuntu. On top of that, we have GPU-specific libraries like CUDA, which really is the API that allow programmatic access to the GPU hardware. And then on top of that, cuDNN, which is a DNN library on top of CUDA. Similarly, for CPU, we have mass libraries like MKL from Intel or open source equivalents. And then on top of that, we can build deep learning frameworks like CNTK and MXNet. So this is very neat, very clean stack. But if you look at the time that data scientists spend on a day-to-day basis, building a model or doing deep learning is only taking a very small percentage of their time. Most of their time is spent on data wrangling. They need to ingest data from different data sources, SQL, NoSQL, data lake. They need to perform different kinds of tasks, statistics, feature engineering, visualization, data cleansing, ETL, right? So the challenge is not to do one particular task well. It's really to build a set of consistent tools that make this entire workflow really simple and make the data scientists more productive. So towards this end, we're developing a Microsoft R server to meet this, right? And in particularly, all the tasks, all the boxes you have seen here can be done at Microsoft R server very easily. Today, what we're going to really want to highlight here is how to do deep learning with GPU with other tasks within the framework of Microsoft R server. Specifically, we're going to show training acceleration with GPU of deep learning on the cloud. And then we'll do massively parallel scoring using HD-Insight Spark. And all the data will be read and stored from Azure Data Lake Store, which provide petabyte scale of data storage. So first thing to set up GPU in the cloud. When you have this N-series GPU instance, you can build it from the bare metal. The step is pretty simple, right? You download CUDA, cuDNN, MKL, all the related libraries from different vendors. You clone the Git from MXNet and configure and build. You're good to go in about 1 hour. And it is actually an interesting process, especially if you want to know all the nitty-gritty details of setting this up and have full control of configuration if needed. And the nice thing is that on Azure, you can, after you are all set with your instance, you don't need to repeat this 1 hour configuration over and over again. You can snapshot your hard disk drive and then store it somewhere on Azure, and then when you want to spin up another instance, you can just rehydrate the instance from that copy. And that's really just 1 or 2 commands on Azure. So I'm going to quickly show you how that looks like here. So this is the tool called Azure Command Line Interface, and it is a cross-platform tool. You can install the same thing for Linux and Mac OS as well. And this command really is the command to rehydrate a GPU VM. In this case, I'm using the largest VM instance that we have, 4 GPUs, NC24 here. And with one command, it is spinning up and on the back end to run the so that you can have access to a powerful GPU VM in a couple of minutes. So I'm not going to wait for this to complete. Let me switch back to the presentation. So, but for a lot of people, even that 1 hour can be saved. You just want to have the raw power of GPU. For these data scientists, we have built an extension of deep learning for our data science virtual machine. Data science virtual machine is one type of instance that we have on Azure that's built specifically for data science workload. We have pre-installed Microsoft R Server, Python, Jupyter, Visual Studio Community Edition, Power BI, SQL Server into the VM. So once you have the instance up, you have that all those tools accessible. For machine learning specifically, we also added Wappel Wabbit for online learning and XGBoost for gradient boosting. And now, when you spin up the DSVM running on top of the N series GPU instances, you would also have all these drivers installed so that you can run your deep learning tools through MXNet and CNTK directly. So with that, I'm going to ask Max to run the MXNet on DSVM and also run through a complete example of deep learning on top of GPU VM as well as HD Insight.
Thank you, Tao. So we created this link where you can access a GitHub page and spin up a data science virtual machine with literally just one click. This is the page. You click this button. Once you click this button, the link takes you to a portal, Azure portal, with a preloaded template where all you have to do really is just enter your username, password, the type of virtual machine that you want. NC6 comes with a single Tesla K80 GPU. NC24 comes with 4 Tesla K80 GPUs and 24 hyper-threaded vCores. So you have massive computing power. Then you basically just enter your subscription, the resource group, location of the VM, agree the legal terms, and press create. So in the interest of time, we've already gone ahead and created this virtual machine. And the data science virtual machine comes with MXNet library already preloaded, and comes already with a preloaded set of examples. So in this case, we're showing a simple Cypher10 dataset training. You can see the NVIDIA SMI command showing you that you have 4 K80 GPUs. We are running at roughly 77% capacity on GPU number 0. And we're running through Microsoft R Server R script executable. On the left, you see the training iterations, and you see basically epochs 1, 2, 3, 4, and so forth. And you see batches evaluate training accuracy per batch, and then give you a validation accuracy at the end of each epoch. So that's it's very easy basically to get started with MXNet on data science virtual machine on Windows. Now we're also going to demo a slightly more complicated example of a data science virtual machine on a Linux data science virtual machine, Azure NC24 series GPU VMs. So this example we're going to describe in more detail later in the talk. But the data set is about 1.6, 1.8 gigabytes of 32 by 32 tiles and images. And what we're doing is we're using R script on the right-hand side to start the training. We point the algorithm to the data directory where the data is stored. We're specifying 20 epochs to run for. And the model is also snapshotted to hard disk after each training iteration. So if you want to adjust things like you want to switch training set and retry conversion, so you want to change the learning rate or momentum, you can do it literally at any point. We're running this on a single GPU, but MXNet can also run distributed mode across 4 GPUs. So once you start this, you should see MXNet initializing. You should see eventually the program appear in the NVIDIA SMI monitor. We also have a blog where we describe this exact process, how to build MXNet on the Azure NC24 series or NC6 series VM, and how to install dependencies such as the Intel Math kernel library, CUDA, cuDNN, and well, pretty much everything that it needs. So you should see a slight delay once it's getting initialized with the GPU. Once it gets initialized, you pretty much have bare metal speeds on the GPU. So while we wait for that, I'll just go back to the presentation. The overall framework, this is basically what it looks like once it's running, right? You have, in this case, we have a larger data set, so it starts off with a lower training accuracy. This is just the first epoch. And as it's batching, you can see the initialization. It's initialized also on GPU number 0. We're using 90% roughly of the GPU. And the whole training here on something like 1.7 gigs of data takes just under 20 minutes to get to 99.7% accuracy in the training set. And we can push this further, obviously. So running MXNet with Microsoft, you can also run MXNet with Microsoft R Server. actually Microsoft R Server with HD Insight Spark is called HD Insight Premium. So if you heard the term HD Insight Premium, it's referring to the same thing. The overall stack is described as the following. You have the underlying storage layer, where you have the Azure Data Lake Store. Azure Data Lake Store is really a collection of automatically striped Windows Azure Blob Storage accounts. So basically, you don't have to worry about ever partitioning your data, striping your data across multiple HDFS accounts. That's already done for you. Another advantage is that Azure Data Lake Store has data schema position on read. So basically what this means is you can toss your data onto the cloud, onto Azure Data Lake Store, and not worry about imposing a schema until you actually want to get the data. So you only worry about imposing schema when you actually get the data on read. HD Insight Spark cluster runs on Ubuntu Linux. And the Spark cluster default setting comes with 2 head nodes, a bunch of worker nodes. You tell it how many worker nodes you want. And Microsoft R Server runs on an additional node, which we call the edge node. It's in the same virtual net of the cluster, so it's in the same firewalled environment. And Microsoft R Server is installed also on all the worker nodes of the cluster. So this is the overall architecture. Now, spinning up a cluster is just as easy as spinning up a data science virtual machine, which we just showed you. Basically, the only difference is you would spin this up as any other Spark cluster. The only difference is on the slide on the left side of the slide, you would select R Server on Spark, and you select premium hardware. By default, right now, this comes with Spark 1.6, but Spark 2.0 isn't too far behind. And on the right-hand side of the slide, you see the hardware configuration. You can have a lot of different types of virtual machines. Default configuration provides you with 4 D4 nodes. But if you really want to push the boundaries, you can get D14 V2 virtual machines that have 16 hyper-threaded cores and have 112 gigabytes of RAM. So there's plenty of computing power. Also, once you've spun up the cluster, you can resize it. You cannot change the underlying hardware that you choose in this step, but you can scale the number of worker nodes up and down as you want. And of course, before you create the cluster, it shows you how much cost you're going to incur. Because if you run many D14 V2 nodes, it may get expensive for you. So you also get an automated cost estimate. So we're going to proceed with the example next, and we're going to describe what we're showing, the actual demo we're going to show you guys, and how we're doing it and what data we're working with. So we start with the Cypher-10 dataset. Cypher-10 dataset was mostly built by Alex Krzyzewski at the University of Toronto around 2008, 2009. It's a data set of 60,000 of these small tiles. They are 32 by 32 pixels each, and they're RGB. So you have 3 channels, red, green, blue for the color, and then you have dimension 32 by 32. And there are 10 distinct classes that are mutually exclusive. So there's airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And notice that both cars, automobiles, and trucks, they don't include SUVs or pickup trucks. So there's no overlap. Trucks include specifically heavy machinery like fire trucks or cargo trucks or dump trucks. And so the original formulation of the problem is you train the neural network to classify, given another image, whether it falls into one of these 10 classes. Well, we want to make things a little bit more interesting. So by now you're probably wondering why I'm showing you a picture of, you probably all know who this is. This is the Mona Lisa. This is the painting from early 1500s by Leonardo da Vinci. And we decided to make things a little bit more interesting, so we created our own Mona Lisa. So this is our test subject plus the Cypher-10 test batch, where what we've done is we created an image of Mona Lisa from the Cypher-10 tiles. And so if you zoom in on the nose of Mona Lisa, you can see that there's a car on the nose, and there is no car anywhere else in the picture. And if you zoom in on Mona Lisa's left shoulder, you can kind of make out there's one car, there's a boat, there's another car. So basically what we want to do is we want to ask you to identify all cars and all boats in this image. And notice that the problem is getting kind of complex because the tiles are overlapping. So it's unreasonable to expect a human or a machine to figure out if there's a car tile being hidden behind some tiles if, let's say, only 2 pixels are visible, right? It's impossible to tell. But in some cases, like in this case, we can actually see that there's actually a car tile, right? So for a human, if I asked you to take a high-resolution picture of Mona Lisa made out of these tiles and give me a list of all cars and all boats and the exact locations of where they are in the image, it would probably take you a very long time, right? But we usually take it for granted that when we look at a vehicle, we see that it's a car, right? So if you heard of the ImageNet competition, right, it's easy for a human to identify a car. In this case, it's not so easy for a human, but it's very easy for a machine, right? So we're going to sort of give you an overview of how we went about solving this problem of finding all cars and boats in this picture. The overall stack is exactly how we described it earlier. We have the underlying Azure Data Lake storage layer. We put this generated tile of Mona Lisa. And by the way, we don't know where the cars and boats are ourselves. We use a third-party program to generate that image. So we don't actually know the true answer. So we generate this image, we put it on Azure Data Lake storage, and in the output data set, what we want to generate is this exact image, and we want to put bounding boxes in red around cars and in green around boats. And we don't want to put bounding boxes if it's not a car or a boat. We just want to leave it blank. The training data is the original Cypher 10 data set. We can also put it on Azure Data Lake Store, although eventually we'll have to remigrate it to the NC24 GPU VM with MRS. And we tried a few different models. So having 4 GPUs on that is quite handy because you can basically run train models in parallel and select which one does best. We've also done some data pre-processing. If there are some vision guys in the crowd, you'll know that it's important to not fire the bounding box on a negative. So if I show overlapping tiles of, let's say, a truck and a horse and a frog, I don't want the algorithm to think that it's a car or a boat, right? So we had to do a lot of pre-processing, and we actually inflated the data set from, I think the original data set is something like 180 megabytes. So we inflated it up to, I think, 1.7 gigabytes or something like that. And we can actually generate more of these synthetic data sets so that the algorithm trains properly. The training, we did very basic training on Azure NC24 VM. With GPU, it takes less than 20 minutes to get 99.7% accuracy on a training set. Once the model is ready, we do a model export. And here you can put the model back onto Azure Data Lake Storage, or you can just put it directly on the file system of the HD inside Spark cluster with MRS. What we've also done is we've developed our own script action, which allows you to install MXNet across the entire Spark cluster. So basically, once the cluster is provisioned, we submit a script action, which then downloads and installs MXNet on all the worker nodes of the Spark cluster and on the edge node as well. And actually, Microsoft R Server has its own script action. When you create a new cluster with MRS, that's exactly how it does it. It has its own script action that installs across all the nodes of the Spark cluster. So the whole thing is obviously, as you probably guessed by now, is orchestrated by Microsoft R Server. We're using it on the GPU VM, we're using it on the Spark cluster, and we run everything, training, data pre-processing, scoring through Microsoft R Server. So before we show you the final results, we just want to explain sort of why convolutional neural nets really work so well and why we're using CNNs for this problem. So what I've done here is I took the exact same original image of Mona Lisa, and just by hand, I applied a convolution filter to it. And the values of the convolution filter in this case, it's called a sharpening filter. So basically what it's supposed to do is make any kind of edge detection in the image very easy. It's supposed to sharpen up the image. But you notice that this edge detection isn't that great. And the reason why it's not great is because I'm human and I haven't tuned this in any way, shape, or form. I'm literally taking this matrix and I'm multiplying the pixels in the image on the left, and I get the image on the right. Plus I'm rescaling to get the color to come out, right? Next up, I'm showing a blurring filter. And you're probably wondering why I'm showing you a blurring filter, because who wants to have blurry eyesight? Probably no one, right? So blurring is another operation that's very important because although we cannot see individual details in the image, we can learn very general patterns. So for example, you can see that the left-hand side of Mona Lisa's hair sort of, well, that region is the left-hand side of Mona Lisa's hair. That's one area. You can clearly see that you have the top left part of the Mona Lisa's left arm. The forearm is in different shapes. So you can learn these very general shapes by using a blurring filter. And all I did is just change the values in this convolutional matrix that I'm applying to the image on the left, right? So if you do enough of these filters and you optimize them, you get a convolutional neural net. And what we're showing here is this network is one of two MXNet networks that were also built by the same guy who showed, whose data set we showed earlier on. He actually runs two of these networks, but we were just showing one here. And you can see that there are different layers. And as the algorithm progresses from left to right, different layers learn more and more complex features. So for example, the max pooling layer on the left here, this learns edges and blobs. And this is what I showed you earlier in the first few pictures. So what I was trying to do with my sharpening filter, this algorithm does much, much better because it's actually learning how to sharpen the image as it's doing the sharpening, right? So that's the best way to think about it. And similarly, blurring. It's also learning how different colors are located in the image, where you have chunks of them together, and where are the different areas in the image. As you progress through the neural net, it's also starting to learn more complex patterns like texture, which is very important. Then we also have some data-driven numerical features and parts of objects. This becomes more and more important as we're trying to classify that a part of the image is a car. Even if you don't see the whole car, you can see just a part of the car, and you can kind of infer that that's probably a car being overlapped by some other tile, right? And finally, as you progress through the network, you end up with full objects. So what we're showing here is there's a plugin on GitHub by MIT where you can visualize different layers of neural nets as you build them. The original neural net was from MXNet that was used in the ImageNet competition. Let me give a link to the paper below. Next, we're going to describe what we actually used. If you guys remember Joseph Sirosh's keynote, he mentioned Microsoft Research has a new ResNet neural network. That's exactly what we used here. What we're showing here is the 34-layer, so the rightmost network is a 34-layer residual neural net. We actually only used 21 layers in this example. That was good enough to give us a good accuracy, and we don't want to overfit on the data. So the advantage of ResNet is as you go through this network, if you go back to the previous slide, as we're going through the network, deeper and deeper layers allow us to learn more and more complex features. So we want to have the network that's as deep as possible. But there are sort of two problems. One problem is you can massively overfit. And Alex Krzyzewski has a technique for doing that, where he basically uses a dropout technique during training, where he cuts certain neural connections at random. And that's kind of the equivalent of regularization. But if you do that on this network, well, I don't actually know how well it's going to work, but what ResNet does is they actually do these shortcut connections. And so what it allows you to do is, as the algorithm is training, it can figure out which section it wants to train first, what features it wants to learn first. And so you can build a very deep neural net, and you don't have to particularly worry about it not training initially. So it gets easier to train, and with depth, you learn more and more complex features. And that's how we're getting very good accuracy in just under 20 minutes. Yeah, basically, these shortcut connections are mathematically, you can think of them as residuals. But for all intents and purposes, you're literally just shortcutting the convolutional filters. So next, we're going to show you an actual demo of how we're scoring the trained models. Once the model is scored, we are going to go to the edge node of our Spark cluster. And so what I've done here is my address is localhost port 8787. I did an SSH tunnel to the edge node, and we're running RStudio R server. And the code is very simple. First, we have the storage prefix, which is Azure Data Lake Storage, where we place the test image of Mona Lisa. And you can actually access the storage account right here. We see Mona Lisa _ test.png. So we download the image from ADLS onto the local file system. That's the copy to local function. Then we define, so this particular cluster, I'm using 12 worker nodes. So we slice up the operation in parallel to 12 parallel tasks. We load the ImageR library, which we use for image processing from Microsoft R Server. And then we prepare the commands. So we define a step size. I'm going to have a 32 by 32 image tile that I'm going to step through image and cut up the overall test image into many, many small chunks in parallel. And then I'm going to score them, recording the x and y coordinate, return back the results, and label the final image. So here all we're doing is we're just preparing data and the scoring. And then there's a giant function called processImage towards the end here. And this is the function that's going to get parallelized to Microsoft R Server using RxExec. So I'm going to skip it for now. I'll come back to it. There's a lot of code here. I'm going to go back to looking at the results. So the results, this is really how I'm invoking the function. So RxExec is a Microsoft R Server function. I handed the function that I defined, processImage, and I gave it a parallel list of commands, element arguments. Element type nodes, I'm telling it to run at node level. So the way our Spark cluster is initialized in this case, we set the Spark parameters so that you have one executor per each worker node. So I know that if I have this, I'm going to have one of these functions run per Spark worker node. And the length of the arguments, which is 12, because there are 12 nodes. And that's it. This is really the entry and exit point. You get a nice list of results at the end when this finishes running. And then all we do is we just label the image. We get the results and we do the labeling. By the way, if you go back to the top of the script, setting the Spark configurations from MRS is extremely easy. All you do is just execute Rx Spark, and you set your driver size, number of executors, executor memory, and so forth. So to show you guys the final results as we run this, this is the image, and it's cut into 12 vertical chunks. So I send each chunk to the worker on Spark. And so each chunk is processed in parallel. And if you run R server, the output looks something like this. You see the results. That's the RxExec function that I was running. And you see 12 tasks, 0 failed. There are 12 tasks total, 12 completed. It basically orchestrates the results across the Spark cluster and then returns the results back to me. So it's actually very easy to get running on Spark. You don't ever even leave the RStudio. So getting back to the presentation, I want to see how good our results are. Just on a different slide. So next, we want to basically see how we did it, what kind of performance we're getting on this. So this is the test image. Yeah. So you can see that if you zoom in on the image, for example, we're showing the part on the top right of the image where we see a car, but the car is being overlapped by a bunch of images that are not cars or boats. We have a cat, we have, I think, a bird, we have a horse. So this worked great because the reason why I see 2 bounding boxes is because I remember that I'm moving in stride of 16 pixels. So as I'm moving this bounding box of 32 by 32 across, part of it, one of the boxes overlapped part of the car. It said, yep, there's a car there. And another image, and another box overlapped part of the car as well. And it said, yep, there's a car there as well. So that's why we see 2. And we can do clustering to sort of figure out exactly where the car is, right? We don't know exactly where the car is on a test set, even ourselves. But as a result of running this, we can figure out exactly where the car is located. And similarly for the rest of the images, you can see on the Mona Lisa's left arm, there are cars and there are boats. Actually, when I was working on this problem, when I got the first set of results, I had a hard time myself figuring out where the cars and the boats are. But then, as I'm looking at the labeled images with MXNet, I can see, yep, there's actually a boat there, there's a car there. So it worked pretty well. Also, similarly, on Mona Lisa's right hand, we can see there's a car there, the algorithm fired, there's a boat. So the results really work. The results are great, and we got this done very quickly. Runtime across a Spark cluster is something on the order of like 5-7 minutes. And we can improve this runtime easily by just rescaling a cluster. So if you give us a larger panoramic image and that is also made of these tiles, and you want to run faster, well, all you do is you just go to the portal and you increase the number of worker nodes. You wait for the Spark to rescale, and then you rescore in parallel, and you get back the results faster. So in summary, GPU and big data really unlocks deep learning's potential, and to train these deep learning neural nets, you really need to have big data. The data set we're using here is 1.7 gigabytes. That's only scratching the surface of what we can do. That's really like the lower bound of how much data you need. You really need a lot of data because, as you can see, these neural nets, they get pretty deep. And they can learn pretty complex patterns. So you really want to have strong signal and data, and you want to have lots of it. Also, the future is that most of the data will live in the cloud, and that's why we're showing Azure Data Lake Store. You can put your data there. You don't ever have to worry about imposing the schema as you're putting the data, which is usually the case with most database systems. You only have to worry about imposing a schema when you actually figured out what you want to do with the data, where you actually read it out. Also, you're not running into performance issues. Spark is very, very bandwidth hungry. So you can easily saturate the storage of a single HDFS or WASB storage account. Even though the account is designed to handle about roughly 500 terabytes of data, as you're ingressing data in and out, you can easily saturate the bandwidth of a single storage account. So the solution is basically you go and you stripe your data across multiple storage accounts. Well, Azure Data Lake Store already does that for you. So you don't even have to worry about that. Overall, we're integrating everything with Microsoft R Server. So again, you don't even have to worry about leaving the shell of R. Everything's done through R. You still have access to all the open source tools, like we were using ImageR and MXNet. And you also have proprietary Microsoft R Server functions, like we're using RxExec to orchestrate across a cluster. And we're also using Rx Hadoop copy to local to copy the image from ADLS and back up again to ADLS. And similarly, for Azure GPU VMs and Azure Data Science virtual machines, we also show how that works. Obviously, MXNet, we have a blog on how to build it on Linux. So if you ever want to do your own development with MXNet, we have a full write-up on how to get started with that. And if you're just very impatient and you want to get just started using MXNet, as we showed you, you can go to GitHub page, click a button, and you'll have your VM with MXNet on all the examples already preloaded. And of course, there's Data Lake Store if you want to store any kind of amounts of data. So the applications of deep learning, they don't just focus on computer vision. That's just only one small demo that we did in this case. You can extend this to optical character recognition, like OCR. We also have computer vision API at Microsoft. Surveillance applications, like, for example, baby monitor or security. Medical diagnostics, medical images. So computer vision itself alone already spans a lot of different areas. There's machine vision, there's video, there's a ton of different applications. But also you can use the same techniques to speech and natural language processing. Usually you also hear the term like NLP. That's what NLP stands for. So one cool example is machine translation, which was mentioned earlier with real-time translation on Skype. This was mentioned in the CNTK talk, where people can communicate in different languages. To sort of break it down, there's literally a few algorithms there. There's speech to text. We try to just learn what the person is saying and put it into text. And then there's the other part where you take text and you want to learn deep neural networks on text. And to do that, you have to do some pre-processing and reorganization of the data. You can use, actually for text, you can use something very similar. You can actually run ResNet that we showed in this demo on textual data. What you do is you basically map text and strides of characters to a sparse binary representation. And then you can basically think of it as an image. And you can run the same way. And similarly, there are other domains in finance, for example. Some hedge funds, they're using machine learning to scan satellite data. And they learn that if a certain retailer has a lot of cars parked in front of it, they can figure out the financial well-being of the company, and hence if it's a good investment or a bad investment by looking at this data set that seems unrelated, but it's actually very useful knowledge, right? So you can also do these sort of hybrid approaches, financial transactions, to use machine learning to a certain extent. Also, the latest trend is training automation. As I mentioned earlier, a lot of these data sets, they're really massive and they require quite a bit of effort to prepare them. Even in our simple demo, we had to go and prepare a synthetic data set from Cypher10. We couldn't just use Cypher10 directly. So with reinforcement learning, basically letting the machine train by itself, which boils down to basically generating a training set as a machine is training. So a good example of that is, for example, video games. if you want to teach the machine how to play a racing video game with cars, you can just let it try and it will fail, and eventually it'll learn how to drive. But by doing so, as it's trying to play the game, it's really generating a training set, right? So you can either go and generate a training set of what we can and cannot do, which will take you a long time, or you can write a reinforcement learning framework and just let it go and let it learn on its own. So this is the latest trend that's moving out of academia now into the industry. For additional resources, like you mentioned, you can read our blog. And the work that we showed in this demo with Cypher 10 is going to be published very soon. So that's going to be a sequel to the earlier blog of getting set up with Azure GPU series VMs with MXNet. You can also sign up for Azure GPU. You can try it out. And like you mentioned, if you're very impatient, you can just spin up your own data science virtual machine with everything already preloaded. There's also a very good deep learning talk on residual neural nets that we've shown in this demo. There's a link to a YouTube video. And the same MSR guys also have a document on deep learning methods and applications. And also our colleague, Brandon Rohrer, he has a great video on sort of the deep learning 101, how to get started with deep learning. It's also on YouTube. And finally, we also want to acknowledge a very long list of people who helped us with this demo and getting set up with MXNet. We want to thank all the people on the list from our peers and people from the Azure VM team, Data Science Virtual Machine, Microsoft R Server. And we also want to thank the MXNet core developers, KK at Indiana University and Tianqi Chen at the University of Washington. Thank you.